You could have lived through 2 o'clock twice. Yeah.
So we left off, I think we just did one example, right?
What?
On Friday?
Oh, with saddle points? Yeah. And like finding maximum.
All right, so let's try just one more. Come on. Focus. Still fuzzy. That's better. Okay. So let's say f of xy equals 4xy minus x to the 4 minus y to the 4. Take a minute or two, run through the whole process. See if you can apply what we learned. Was it Friday? Yeah. Friday. To this problem. Let's see. We have Jacob, Brian, and who else is not here? Brandon's usually late, but he's here. Andrew. All right, you guys ready here? Or?
No. Wait, now I know. So it's 1. So is that like all the combination of all the x's and y's that we find? Because I don't find exactly like points.
Well, no, you should have.
Can you have multiple? How many of them?
There should be 3 of them.
3? I had like more than 3.
No.
Wait, no, I don't. Wait. Yes, I do. I have 1, 2, 3, 4, 5, 6.
Well, let's go through it.
I'm not embarrassed.
Did we at least all take partial x?
Yes.
And did we all get 4y minus 4x cubed?
Yeah.
Okay. And when you did partial y, you get 4x minus 4y cubed. Now, if we set these to 0, and here we get y equals x cubed, and x equals y cubed. So let's see, what did I do? I plugged in x cubed into here. See, that's what I did. So x is going to be x cubed cubed, right?
Yeah,
so then we get x to the 9 minus x, factor out an x, you get x to the 8 minus 1. And then here you get 3 critical x values. X equals 0, x equals plus and minus 1, right? So those are the 3 critical points you're going to get. Now you just have to find what the y values must be. If x is 0, go back to y equals x cubed. What does y have to be?
0.
And then y here would be 1. So we have this one, that one, and if x is negative 1, then y is negative 1. So those are our 3 critical points. And what did we do last time? D equals partial xx partial yy minus partial xy squared, and then we paid attention to partial xx. Okay, so we should probably go ahead and do that. Partial xx would be partial yy, negative 12y squared, and we just need the mixed partial, which would be 4. So now plug in these 3 values into partial xx, multiply it with partial yy, and subtract partial xy squared. When you do that, you get, for the first one anyway, what? Negative 16. And now partial xx we don't care about. It's just a saddle point. If d is less than 0, it's a saddle point. If I plug in 1, 1, we get 144 minus 16 again, which is definitely greater than 0. But now partial xx would be negative 12, so what does that mean? Good. And same scenario with negative 1, negative 1. Okay, so again, to recap, here's what we want to figure out. We want to determine whether this is a positive or a negative value, and depending on which of the 2 cases we have, we may need to also inspect what partial xx is doing. Once you find partial x and partial y, that's how you get your critical points. Set them to 0, right? And the rest is just plugging everything in, so I don't know. Are there any questions? Yes?
So like a saddle point comes with a hyperbolic paraboloid?
Yes, a hyperbolic paraboloid would give us a saddle point.
are hyperbolic paraboloids always only gonna have 3 extrema?
That's an excellent question. For our typical case, yes.
Okay.
I mean, you could contrive some sort of surface where it's not just this, the normal function, but where it's like, I guess you could say piecewise, and you have several different surfaces together. But yes.
Okay.
hmm Other questions? Okay. Let's move forward. So all we've done is find saddle points, relative maximums, and minimums. Let's talk about finding absolute extrema on a closed and bounded set. Okay. Now, basic procedure is going to be pretty similar to what we did. One, find critical points in the region R. The only difference, and I think you guys can guess as to what's going to come next, when you had a closed set in Calc 1, an interval, right, instead of the entire function, what did you also look at? Endpoints. Well, we don't have endpoints per se. We're going to have a boundary line or a boundary curve. Does that make sense? So we're going to find all boundary points at which absolute extrema can occur. So it's not as simple as plug in x equals 3 and x equals 5 because those are the endpoints. We might have a little bit more going on. That's the only difference. The rest is still the same. Evaluate f of x, y at all the points. Okay, so once you have your critical points and once you've tested the boundaries, not just the endpoints, but the boundaries of the region, then you will be good to go.
What is the number 1?
Oh, R is usually what we define as the region. So they would define, let R be this closed and bounded region defined by blah, blah, blah. So let's actually do one of these. Say f of xy equals xy minus 2x. And we want to find absolute max and min on R, which is defined as the triangular region using the endpoint 0, 0, I should say vertices, not endpoints, 0, 0, 0, 4, and 4, 0. Okay. What about the z component? That's what we're trying to determine is absolute z, absolute max for z, absolute min for z. Yes?
So, when we were doing this in 2 dimensions, we were concerned with like local extrema on the endpoints too. For 3D, is it just going to be absolutes?
It'll be absolute max and absolute min.
Or like
Yeah.
not local, like relative.
Right. Well, if you have a closed and bounded, I mean, you're still going to, the procedure is going to be the same. So, like, all the other points that are not the absolute min and absolute max, those would just be relative extrema
But
by
like
default.
here, like we're finding absolute extrema by definition. So are we? If it's like a relative, do we just not list it?
Yes,
Yes,
we don't list it. You would just say, this is the absolute min, this is the absolute max, here's where it occurs. Now, if they asked you about the other ones, like define relative min or max for those, then you could do the test. Okay. So first, we should find critical points So what's partial x?
1 is 2.
And partial y
X.
is x. Set these both to 0. What do we get?
X equals 0. Y equals 2.
Okay, so that's interesting because, let's see, here's our region R. 0, 0, 4, 0, 0, 4. Where is 0, 2? It's on the actual boundary, right, on the triangle. So this is actually not in R, so it's not on the interior, so we're not going to worry about it right now. Now, if it was on the interior, then we would keep it. But since we're going to test the boundaries anyway, we're going to ignore 0, 2. Maybe it comes up, maybe it doesn't. Okay, because what's going to happen is as we test this boundary from 0, 4 to 0, 0, when we find any critical points here, if 0, 2 is the way to go, then 0, 2 will come up as a critical point. Otherwise, we would just use the endpoints. Okay? So since that's the only critical point we would get, but it's not in R, then the second thing we do now is we test the boundary points, or the boundary lines. So if we test, let's do this side first. What's the equation for that side of the triangle?
X equals 0.
Let's actually write them all down. X equals 0, this one would be y equals 0, and this is? Good. So those are the three things we're going to check. So now along x equals 0, what's f of xy going to be?
It's 0.
It's just going to be 0. Which means then that when you do partial x, it's automatically 0. There's no x value to set equal to 0, so there's no critical points on the boundary itself. Okay, so we're still going to use 0, 0, and 0, 4 though. Okay, but there's nothing on the boundary. Let's see what happens along y equals 0. Along y equals 0, what do we get? F of xy is negative 2. Partial x will be negative 2, but we can't set that to 0 and solve for anything, so we get the same conclusion here. No critical points between the vertices along y equals 0. The last piece is along y equals negative x.
Shouldn't that be y equals negative x plus 4?
Yes, it should be. Negative x, thank you. Not only is it a negative x, negative 1 slope, but we do have the y-intercept that we forgot about. Thank you. So now along y equals negative x plus 4, let's figure it out. F of xy will be x times negative x plus 4 minus 2x, which gives us negative x squared plus 4x minus 2x is just plus 2x. Alright, so now we do have something to work with here, because if we find partial x, what do we get?
X. Negative 2x plus 2.
Which gives us that x has to be 1. And now since, I mean, we could go ahead and find partial y if we needed to, but the important thing is we know what y is already. Where is it? Y equals negative x plus 4, right? So what does y have to be? 3. Okay, so in addition to 0, 4, 0, 0, and 4, 0, Nothing on the interior to worry about, but along y equals negative x plus 4, we also obtained 1, 3 as another critical point to test. So there are 4 of them. So let's do this way. So the critical points I'll put up on the top. We have 0, 0, 0, 4, 4, 0, and then we also obtained 1, 3.
And how do you know that those 3 points are...
How do I know that these 3 points need to be included? Optimization principles. I don't know if you remember anything about linear programming and stuff like that, but anytime you have a region, so let's just take the simple case where you have, let's say, a plane like this, right? Like that. Is it clear that the corner points, 1, 2, 3, 4, one of those 4 corner points will be the absolute max, and one of those 4 would be the absolute min.
so you still haven't like confirmed.
Right. The thing is, we don't know what's going on from here to here. Is it maybe increasing and coming back down, which is a possibility? Does that make sense? But for sure, we have to include all the corner points. Okay.
So what about 0, 2?
0, 2, it didn't make a difference because it was along the x equals 0 plane. So you can almost think of it as, so like here's a corner point, here's a corner point. 0, 2 ends up being in between, so it's not going to be either a min or a max.
Oh, so is it a relative?
It would be a relative one, yes, but not an absolute. Yes?
For like along x equals 0 and along y equals 0, you plug in y equals 0 into the equation.
Yes.
Take the
And then take partial x.
partial x of y equals 0.
So you go back to f of x, y, and as you're checking, when you check the boundary paths, you actually plug the path into f of x, y. So when we checked x equals 0, we actually plugged 0 into x for both of the terms. And that's where we got our new function is f of x, y equals 0, which doesn't do anything for us. We did the same with y equals 0. We got negative 2x, which is slightly better, but when you do the partial derivatives, it doesn't give us any critical values. Does that make sense?
Does it matter which partial derivative you take? Does it always have to be partial x?
No. I mean, you could do either. The thing is that you want to include, you have to include both somehow to get a critical point, right? So I usually go partial x, especially if we have things defined already in terms of y, because we know what y is going to be automatically. So really all we're after at this point is what is that critical value for x going to be? Because once we have x, y will just be negative that plus 4 automatically. Or, you know, depending on where we are. Does that make sense? Okay. All right. So sorry. Maybe some of you already have this. What values do we get? 0, 0, negative 8, and 1. Okay? So then, absolute max is 1, absolute min is negative 8. That's it. You plug them back into f of x, y.
How do we get 1 for 1 comes 3? Wait.
Yeah, 1 times 3 is 3. 2 times...
Oh, 1, yeah.
So that's it. I don't know either.
You got a 2 in there?
Okay. Now, we could actually, you guys raised some great questions. What was the other point that we almost used? 0, 2. And judging it from the stuff that we just discussed, right? What would we expect for 0, 2? Well, somewhere in between, right? Max and min. If we plug 0, 2 in, you guys can't see that. If we plug 0, 2 in, what do we get? Yeah. So don't have to worry about it. Okay. Any questions so far? Yeah.
So you said we didn't use 0, 2 because it was kind of in between like 0, 0 and 0, 4.
Yes, not just in between, but it was on the actual boundary. That's the only reason we ignored it, because if we needed to include it, it would have come up when we tested the boundary.
But 1, 3 wouldn't be considered on a boundary?
It is, but when that we obtained 1, 3 from actually testing the boundary. So 1, 3 wasn't a point that we obtained by just the first partials test. It was obtained by, well, so nothing's really going on the interior, but now we got to test the boundaries and see what's going on there, which is a little bit more extensive than in Calc 1, because in Calc 1 you didn't really have a boundary path. It was more of a, well, it's either x equals 0 or x equals 4. Let's test them both and see what happens. Here it's you have to test all the points that are along those paths. Okay. Let's do an application with some constraints. And this example will tie into what we do, not tomorrow, but tomorrow's Wednesday, right? Thursday, when we start talking about Lagrange multipliers. But we don't need them for this problem.
We're not doing it tomorrow? I think that was 13-9.
Did we discuss? Oh, maybe we are doing it tomorrow.
Yeah. You said
That's
that
right.
we
We're
did
going to have
it
2 work days in a row. That's what we agreed to. Okay.
But when you state the absolute max, is it point? Like 4, 0?
It's not a point, so it's like if you were asked to determine the minimum or a maximum of a function, like a parabola, it's just the y value, right? So
But
here
you say that at
you could say absolute max is 1 when x is 0 and whatever the case was, yeah. But if it's just a matter of what is the absolute min, what is the absolute max, then all we're looking for is the output, the z value. Okay, find the dimensions of a box. Open at the top. Having volume equal to 32 feet cubed, requiring least amount of material.
Is V just 32?
Yep. So, what else do we need here? Yep. Well, couple we can write. We know the volume has to be 32, so let's draw a picture in case you forgot what a box looks like. If we position the box, well, actually, we don't have to even position it. Why don't we just call the length, width, and height x, y, and z. So then the volume, which is 32, would be found by x times y times z. So this is the constraint. This needs to happen. And now what we're interested in is the surface area, particularly the smallest surface area possible, right? What would the surface area for the box be?
2xy plus 2xz plus z.
It's open at the top, so it wouldn't be an x one.
Well, you could do it however.
Yeah, so if it's open up here, I guess it depends on how you label the picture, right?
So 2xv plus 2.
Yeah, 2 of everything except xy.
Plus yx.
Yep. Okay. So now the reason why we can,
Wait, you have xy plus 2x.
oh, that's supposed to be xz. Sorry. Okay, so currently we don't have a way to maximize or minimize functions in how many variables is this? 3, right? If it were just two variables, we could do first partials test and be on our way, right? However, we do know this constraint here, that x, y, z has to be 32. So we could use that to our advantage. Get one of those variables that we're not used to seeing, z, and plug in z into the s. So z would be 32 over xy, and then we can rewrite the equation. So we have xy plus, what would this be? 2 times x times 32 over xy. So that'll be 64 over y plus 64 over x. And now we have a function in two variables that we are very good at this point in finding minimums and maximums. So what do we do first? Partials. So partial x will be y minus 64 over x squared. Partial y would be the reverse of that. What I mean is x's and y switched. We set both of these equal to 0. Probably the easiest thing to do would be to say y is 64 over x squared, and now we plug that into the second equation. So we get x minus x to the 4. Oop, sorry, getting ahead of myself here. X minus 64 over 64 over x squared squared equals 0. So that's going to give us 164 in the denominator. The x to the 4 you can put in the numerator. And we solve. Let's see, factor out an x. You get 1 minus x cubed over 64. X equals 0 isn't going to help us. What would x be in the second factor? X would be 4, which then means that y is going to be 64 divided by 16, which is also 4. So this is the only critical point that we have. So what does z have to be? Yep. So there are the dimensions. Yeah. It is a 4 by 4 by 2 box. That's the length, that's the width, and that was the height. This is the only critical point we have. So we're ready to go. Yes?
After you get x equals 4, do you plug that into the partial or the actual equation?
I took x equals 4 and I plugged it into y equals 64 over x squared. So technically we're plugging it into the partials, but I'm using a reduced form of the partials already. Just makes it easier. Okay. Any other questions? All right, I have one more thing to talk about, and then we are done. It's not the proof, sorry. But it's pretty quick and simple concept. It's using contour plots to identify critical points. Okay, so you should be able to look at a contour plot, so look at different level curves, and then say, well, there's probably going to be a critical point here, here, and there. And if you have enough information, you could even tell me what kind of point it is. Maybe a minimum, a maximum, or a saddle point. So we'll just do a couple of examples, and you guys can tell me what you think. So let's say this is the contour plot. And this is 0. This is 1. This is -1. This is 0. That's 1. That's -1. So it's a weird labeling of the x and y axis, but
Are those thingies the same amount?
we don't know. And we don't know, and it doesn't matter. If I ask you, are there any critical points? You would say, where?
0, 0.
Yes. Now, could you tell me what kind of critical point it is? Relative min, relative max? No. So at this point, we can say 0, 0 is a critical point. Now, with more info, which you may or may not have, we could determine whether it's a relative min or a relative max. Obviously, if the curves are, if we start, let's say, at 5 and then 3 and then 2 and then 1, what would you say this would be? Outside is higher, and then we start getting lower, so this would be a minimum. Okay, so if you have enough information, then you can be more specific. Let's do another one.
Is this the last one?
Yep. This is not the best drawing I've ever done, sorry. And let's say that our view for x and y, we have 0, 1, 2, -1, -2, 0, 1, -1. That should be good enough.
Is there a reason for labeling?
Just because if we had the axis labeled within, it might confuse level curves.
Oh,
So it just provides a better view as to what the actual curves look like.
so will we have to draw a curves like that?
No. These will most likely be given to you. So it'll say like, here's the contour plot of some function f of x, y. What can you tell me about it? So let's say this is the contour plot. What could you tell me here? Where are the critical points? 0, 0. Where else?
0, 2.
-2, 0.
Yeah, do you mean 0, 2?
Which one's the x?
X is still going to be this way.
Oh, okay.
Oh.
So it'll be 2, 0, and -2, 0. Now, can you give me any more information?
No. Is the middle one seven?
Yes. 0, 0 must be a saddle point. Now, whether 2, 0 and -2, 0 are mins or maxes depends on what the hyperbolic paraboloid looks like. Okay, so that we can't determine, but whenever you see this kind of figure 8 pattern, okay, you can always guarantee that that's going to be a saddle point. So it's easy to remember. Mm-hmm. Okay. All right. Andre is on Twitter, so I think I'm done. Were you on?